Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the silent depths where interstellar visitors drift through our cosmic neighborhood. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The night sky above Ukraine holds its breath on August 30th, 2019. At the Crimean Astrophysical Observatory, automated telescopes sweep methodically across predetermined coordinates, their digital sensors collecting photons that have traveled unimaginable distances. The ATLAS survey system, Asteroid Terrestrial Impact Last Alert System, performs its quiet vigil, scanning for objects that might threaten Earth. Tonight, like countless nights before, the telescope captures thousands of points of light, each one catalogued, measured, cross-referenced against previous observations that stretch back decades. The observatory sits beneath a dome of stars that have witnessed the rise and fall of civilizations, the formation of planets, the birth and death of suns. Yet, tonight, among all these ancient lights, one particular photon carries information that will reshape humanity's understanding of what travels between stellar systems. This photon began its journey from a surface illuminated not by our sun, but by the reflected light of a star whose name appears in no human catalogue, whose existence remains unknown to terrestrial science. Among these countless stellar whispers, one dot appears unremarkable. Its brightness registers at magnitude 19.6, so faint that the human eye could never perceive it, even through the largest amateur telescopes. The object moves against the background stars at a rate suggesting it belongs to our solar system, perhaps another asteroid wandering the space between Mars and Jupiter. The automated systems assign it a preliminary designation A2019Q4. The A indicates an asteroid. The numbers mark the year and discovery period. Nothing in this moment suggests that this single point of light will soon force astronomers to question fundamental assumptions about matter, motion, and the nature of objects that drift through interstellar space. The discovery image shows only a streak, the object's motion during the 30-second exposure, creating a thin line against the stellar backdrop. This motion speaks of orbital mechanics, of gravitational relationships with our sun that stretch back billions of years to the solar system's formation. Yet something in the mathematics whispers differently. The streak's length and orientation hint at velocities that don't quite match the expected patterns for objects born within our star's gravitational influence. The preliminary orbital calculations suggest an unusually high eccentricity, the kind that marks objects arriving from the solar system's distant edges, the Kuiper belt, the scattered disk, perhaps even the theoretical Oort cloud where comets wait in frozen suspension. In the following days, additional observations accumulate like layers of sediment in an archaeological dig. Each measurement refines the object's position, its apparent motion across the sky, the subtle variations in its brightness. The International Astronomical Union's Minor Planet Center collects these reports from observatories across 6 continents, feeding them into orbital determination algorithms that have successfully tracked tens of thousands of asteroids and comets over decades of systematic observation. The calculations converge slowly, iterations revealing an increasingly strange trajectory that defies conventional categorization. This object approaches the Sun not in the familiar elliptical paths of solar system natives, but along a hyperbolic curve, the mathematical signature of something that has never been gravitationally bound to our star. The orbital eccentricity exceeds unity, meaning the visitor follows an open-ended path that will carry it back into interstellar space after its brief encounter with our solar system's warmth. Only twice before has humanity confirmed such a trajectory. Oumuamua in 2017 and Tuuyue Borisov in 2019. Now a third interstellar wanderer announces its presence through the patient accumulation of photometric data points. The realization settles quietly over the astronomical community like morning mist. This visitor originated beyond the gravitational influence of our Sun, somewhere in the vast darkness between stellar systems where temperatures hover just above absolute zero. Its journey to our solar system may have lasted millions of years, drifting through space so empty that individual atoms become rare encounters. The Discovery team applies for a new designation, and the object becomes 3 Atlas, the third interstellar visitor to receive official recognition from the international astronomical community. Yet even as telescopes around the world turn to examine this cosmic stranger, something else begins to unfold in the accumulating data. The object's brightness starts to increase in ways that asteroid models cannot explain. Simple thermal calculations predict how reflected sunlight should behave as the visitor approaches our star. But 3 Atlas defies these predictions with systematic stubbornness. Spectroscopic observations reveal absorption lines that speak of water and carbon compounds, materials that shouldn't be present on the surface of a simple rock that has spent eons traveling through space where temperatures would freeze these substances into solid ice. The mathematical models that successfully predict asteroid behavior begin to fail, one by one, as 3 Atlas refuses to conform to terrestrial expectations. Newton's laws of motion describe how objects should accelerate under gravitational influence, but this visitor shows subtle deviations that suggest additional forces at work. The brightness variations hint at a rotating body, but the periods don't remain constant like those of familiar asteroids. Instead, the light curves display complex patterns that speak of structural changes occurring on timescales measured in days rather than the billions of years typically required for geological processes. Night after night, the observations accumulate in digital archives that will outlast the civilizations that create them. Each measurement adds another piece to a puzzle that seems to grow more complex rather than resolving into clarity. Professional observatories coordinate observation schedules across time zones, ensuring continuous coverage as Earth's rotation carries different telescopes into darkness. Amateur astronomers contribute their own measurements, adding to the growing database with equipment that would have seemed impossibly sophisticated just decades ago. The object's motion deviates slightly from pure gravitational trajectories, as if some invisible force provides gentle acceleration. This non-gravitational acceleration resembles the rocket effect seen in comets, where sublimating ice creates jets that can alter orbital motion. But 3 Atlas displays this acceleration at distances from the Sun, where water ice should remain frozen solid, where temperatures barely exceed the background radiation left over from the universe's birth. The physics of sublimation cannot explain what drives this visitor's increasingly rapid motion through our solar system. Surface features appear and disappear in high-resolution imaging like mirages shimmering in desert heat. The object's apparent size changes in ways that suggest either extreme elongation or dramatic variations in reflectivity. Thermal infrared observations paint a picture of temperature distributions that don't match any known class of solar system object. The accumulated data begins to resemble not a single coherent picture, but a collection of contradictory evidence that challenges fundamental assumptions about how matter behaves in the cold depths of space. The international network of observers maintains its quiet vigil, recording the strangest passage through our solar system with instruments sensitive enough to detect the heat signature of a campfire on the moon. Radio telescopes listen for any hint of artificial signals, finding only the natural emissions expected from heated rock and ice. Optical telescopes map the visitor's rotation and search for signs of fragmentation or outgassing. Infrared sensors measure thermal emissions that reveal internal temperatures and surface composition. In the data files that grow larger each night, 3Y Atlas begins its transformation from simple discovery to profound mystery. The numbers whisper of processes unknown, of behaviors that will force scientists to question whether their understanding of interstellar objects applies to visitors from stellar systems with different formation histories. Perhaps the physics that governs matter in our solar system doesn't extend uniformly to objects forged in the gravitational fields of alien suns, under radiation environments that Earth-based science has never encountered. Only later will researchers understand that this quiet detection on an August night in Ukraine marks the beginning of humanity's encounter with something that challenges every model of how interstellar visitors should behave. The stranger approaches, accelerating through space in ways that violate established theory, carrying within its mysterious behavior questions that will haunt astronomy for generations. The orbital calculations arrive like whispered confessions from the void itself. In observatories scattered across continents, astronomers feed the accumulated position measurements into software that has successfully tracked thousands of solar system objects for decades. The algorithms converge with mathematical certainty on parameters that should be impossible. 3I Atlas follows a hyperbolic trajectory with an eccentricity of 4, to a number that speaks of velocities so extreme they can only originate from beyond our sun's gravitational dominion. This eccentricity value exceeds that of Oumuamua by a factor of nearly 2, marking 3U Atlas as the most obviously interstellar object ever detected, where Oumuamua's hyperbolic excess velocity measured 26 kilometers per second, the speed it retained after escaping our sun's gravity. This new visitor approaches with energies that suggest an origin from stellar neighborhoods where different physical processes shape matter and motion. The numbers whisper of a journey that began perhaps millions of years ago, when 3I Atlas received its initial velocity from gravitational interactions near an alien star system. The orbital plane tilts at 17 degrees to the ecliptic, that fundamental reference frame defined by Earth's path around the Sun. This inclination places the visitor's trajectory well outside the flattened disk, where planets and most asteroids maintain their orderly processions. Instead, 3I Atlas approaches from the direction of the constellation Draco, diving toward our solar system's heart along a path that intersects the orbital planes of multiple worlds. The geometry speaks of origins utterly disconnected from the processes that shaped our familiar solar system architecture. Astronomers calculate the visitor's closest approach to the Sun. Perihelion will occur at a distance of 37 million kilometers, well inside Mercury's orbit, but safely beyond the solar corona's superheated plasma. At this distance, solar radiation will heat the object's surface to temperatures exceeding 500 Kelvin, hot enough to sublimate water ice and drive off volatile compounds that might cling to its surface. The thermal calculations predict a brightening event as reflected sunlight increases and outgassing begins. Yet the magnitude of brightening already observed suggests processes far more complex than simple illumination geometry. The velocity vectors tell their own story of cosmic exile. At its current distance from the Sun, 3I Atlas moves at approximately 42 kilometers per second relative to our star, a speed that dwarfs the orbital velocities of familiar planets. Earth circles the Sun at a leisurely 30 kilometers per second, while even Mercury, racing through its close solar orbit, manages only 47 kilometers per second at perihelion. This interstellar visitor carries kinetic energies that speak of acceleration processes unknown in our quiet stellar neighborhood. Gravitational modeling reveals the visitor's future trajectory with mathematical precision. After its brief encounter with our solar system's inner regions, 3I Atlas will depart along a path that carries it toward the constellation Lynx, accelerating as our Sun's gravity assists its escape velocity. The hyperbolic orbit ensures this encounter remains temporary, a single pass through our cosmic neighborhood that will last mere months before the visitor returns to the interstellar medium from which it emerged. Yet the numbers also reveal troubling inconsistencies. The orbit shows systematic deviations from pure Keplerian motion, the mathematical description of how objects should move under gravitational influence alone. These deviations manifest as small but measurable accelerations that cannot be explained by the gravitational fields of any known solar system object. The visitor appears to generate its own propulsion, as if invisible jets push against the vacuum of space to alter its trajectory in subtle but persistent ways. The magnitude of these non-gravitational accelerations resembles those observed in comets, where sublimating ice creates reaction jets that can significantly alter orbital motion. But 3I Atlas displays this behavior at distances from the Sun where comet nuclei typically remain dormant, frozen into geological inactivity by the cold of deep space. The physics of sublimation cannot explain accelerations observed when the object travels beyond Jupiter's orbital distance, where solar heating remains insufficient to vaporize common ices. Thermal models struggle to reconcile the visitor's observed brightness with its calculated distance and size. The object reflects sunlight with an efficiency that suggests either an unusually bright surface composition or geometric properties that concentrate reflected light in Earth's direction. Standard asteroid models assume roughly spherical bodies with surface compositions similar to meteorites. But 3I Atlas defies these assumptions with systematic persistence. Its brightness variations suggest either extreme elongation, perhaps 10 times longer than wide, or surface features that create dramatic albedo variations. The mathematical analysis reveals another troubling inconsistency in the visitor's rotation period. Initial observations suggested a rotation every 8.7 hours, typical for small asteroids that have achieved rotational equilibrium through billions of years of minor collisions. But subsequent measurements show variations in this period, as if the object's rotation accelerates and decelerates in response to internal processes or external forces that remain invisible to terrestrial instruments. Dynamical studies attempt to trace the visitor's origin through three-dimensional stellar motion models. The calculations work backward through time, accounting for the gravitational influence of nearby stars and the galaxy's overall rotation. The analysis suggests 3I Atlas originated from a stellar system located approximately 500 light-years from Earth, a distance so vast that the visitor's journey to our solar system required millions of years of drift through interstellar space where temperatures hover near absolute zero. The orbital geometry also reveals why this interstellar visitor remained undetected until its discovery in August 2019. The object approached from a direction nearly aligned with our solar system's motion through the galaxy, creating a slow, apparent motion against the background stars that automated survey systems initially classified as noise. Only when 3I Atlas began its acceleration toward the Sun did its motion become rapid enough to trigger detection algorithms designed to identify potentially hazardous asteroids. Each successive orbital calculation refines the visitor's parameters while deepening the fundamental mystery of its behavior. The mathematics describe an object that simultaneously conforms to and violates the basic principles of celestial mechanics. 3R Atlas follows a predictable trajectory shaped by solar gravity, yet displays accelerations that suggest additional forces operating according to unknown physical principles. The numbers accumulate like evidence in an unsolvable case, each measurement adding precision to parameters that describe increasingly impossible behavior. In conference rooms and research offices around the world, astronomers gather around computer screens displaying orbital plots that challenge decades of theoretical understanding. The visitor approaches our sun along a path governed by mathematics that extend beyond current scientific knowledge, carrying within its trajectory questions that may outlast the civilizations attempting to answer them. The brightness measurements arrive each night like vital signs from a patient whose condition defies medical explanation. Across the globe, photometric systems record the steady strengthening of 3I Atlas as it drifts through the gravitational architecture of our solar system. What began as a faint smudge requiring the most sensitive digital cameras has brightened by nearly 2 magnitudes in just 6 weeks, an increase that transforms the visitor from invisible speck to detectable target for advanced amateur telescopes. The brightening follows no familiar pattern. Standard thermal models predict how reflected sunlight should increase as an object approaches our star, following inverse square laws that have governed astronomical brightness calculations for centuries. Yet 3I Atlas brightens faster than these models allow, as if additional light sources activate within its structure. The excess luminosity suggests processes beyond simple solar illumination, perhaps the sublimation of exotic ices or the exposure of highly reflective materials buried beneath a darker surface layer. Observatories coordinate their measurements through international networks that span 6 continents and multiple time zones. The Catalina Sky Survey in Arizona records brightness values each clear night, while telescopes in Chile, South Africa, and Australia maintain coverage as Earth's rotation carries different facilities into darkness. The accumulated photometry creates a continuous record of the visitor's approach, revealing brightness variations that occur on timescales ranging from hours to weeks. The short-term variations suggest rotation, as surface features with different reflectivities pass in and out of view. But these rotational signatures display troubling inconsistencies that challenge basic assumptions about solid body mechanics. The brightness peaks don't occur at regular intervals, instead showing systematic drift that implies either a changing rotation period or complex geometric effects that current models cannot accommodate. Some observations suggest the visitor rotates every 8.7 hours, while others indicate periods as short as 6.3 hours variations that would require impossible changes in angular momentum for a solid object. Spectroscopic analysis of the brightening light reveals molecular signatures that shouldn't exist on an asteroid's surface. Water vapor absorption lines appear in spectra taken when 3I Atlas remains well beyond Mars' orbit, where solar heating should be insufficient to sublimate ice deposits. The presence of OH radicals. Fragments of water molecules broken apart by solar radiation confirms that H2O molecules escape from the visitor's surface at temperatures far below the normal sublimation threshold. These water signatures intensify as weeks pass, suggesting increasing rates of molecular loss despite the visitor's continued distance from our Sun. The spectral lines display Doppler shifts that indicate expansion velocities of several hundred meters per second, fast enough for the escaping molecules to overcome the object's weak gravitational field and disperse into space. This molecular outflow creates a tenuous coma around 3I Atlas, invisible to optical telescopes, but detectable through careful spectroscopic analysis of absorbed sunlight. Carbon monoxide lines also appear in the spectra. Speaking of even more volatile materials escaping from the visitor's interior, These CO molecules require less solar heating to achieve sublimation, yet their presence at such distances from the Sun suggests either unusually efficient heat transfer within the object's structure or internal energy sources that remain unidentified. The molecular outflow rates calculated from spectral line strengths indicate mass loss approaching several tons per day, a hemorrhaging of material that should be impossible for such a small object at its current solar distance. The brightening also displays color variations that hint at compositional changes occurring in real time. Photometric measurements through different optical filters reveal shifts in the visitor's overall spectral properties as it approaches the Sun, initially appearing slightly redder than typical asteroids. 3i Atlas gradually develops a more neutral color signature that suggests either the exposure of buried materials or chemical alterations occurring on its surface. These color changes correlate with the brightness increases in ways that challenge established models of asteroid behavior. Objects that brighten due to closer solar proximity typically maintain constant color signatures unless they experience catastrophic disruption. Yet, 3i Atlas displays systematic color evolution that implies ongoing surface processes, perhaps the sublimation of reddish organic compounds that expose more neutral rocky materials beneath. Thermal infrared observations reveal another layer of mystery in the visitor's brightening behavior. Measurements at wavelengths of 10 and 20 micrometers detect heat emission that exceeds predictions based on solar illumination alone. The thermal excess suggests either internal heat sources or surface properties that trap and re-radiate solar energy with unusual efficiency. Standard asteroid thermal models assume surfaces composed of rocky materials with well-characterized thermal properties. But 3i Atlas radiates heat like an object with fundamentally different composition. The infrared measurements also reveal temperature variations across the visitor's surface that change on timescales of hours. These thermal patterns don't correlate with the expected day-night temperature cycle for a rotating asteroid, instead showing complex distributions that suggest active heat sources or unusual thermal conductivity properties. Some surface regions appear significantly warmer than solar heating alone can explain, while others remain cooler than ambient space temperatures. Polarimetric measurements add yet another puzzling dimension to the brightening phenomenon. Light reflected from 3i Atlas shows polarization characteristics that change as the visitor approaches our Sun, suggesting either evolving surface texture or the activation of scattering processes unknown in conventional asteroid physics. The polarization signatures resemble those seen in comet Comets, yet the visitor displays these characteristics at distances where comet nuclei typically remain inactive. Radio telescopes detect faint emissions at centimeter wavelengths that correlate with the optical brightening events. These radio signals suggest electrical activity within or around the visitor, perhaps the ionization of escaping molecules by solar radiation or internal processes that generate electromagnetic fields. The radio emissions vary with the same periods as the optical brightness changes, implying a physical connection between the visitor's rotational state and its electromagnetic activity. Each night's observations add new data points to brightness curves that grow increasingly complex rather than converging towards simple explanations. The visitor's approach transforms from predictable astronomical event to ongoing mystery that challenges fundamental assumptions about how small bodies behave in interplanetary space. Professional astronomers share preliminary results through electronic circular networks, while amateur observers contribute their own measurements to collaborative databases that document the visitor's impossible behavior. The brightening continues with mechanical persistence, as if 3i Atlas operates according to physical laws that extend beyond terrestrial scientific understanding. In research offices and observatory control rooms, scientists gather around computer screens displaying light curves that violate decades of established theory. The visitor approaches our Sun while generating luminosity through processes that remain invisible to the most sophisticated instruments humanity can deploy. The starlight carries secrets encoded in wavelengths that telescopes pass like ancient texts written in languages nearly forgotten. Across the electromagnetic spectrum, 3i Atlas speaks through absorption lines that appear and disappear in spectral data collected by instruments sensitive enough to detect individual photons, arriving after journeys measured in astronomical units. Each wavelength tells part of a story that grows more complex with every observation, revealing molecular signatures that challenge fundamental assumptions about interstellar objects. The water vapor lines appear first, thin, dark bands etched into the continuous spectrum of reflected sunlight at wavelengths near 1.4 micrometers. These absorption features shouldn't exist at the visitor's current distance from our Sun, where temperatures remain too cold to sublimate water ice from exposed surfaces. Yet the spectral signatures strengthen night after night, indicating increasing quantities of H2O molecules surrounding the object in a tenuous atmosphere that extends thousands of kilometers into space. Hydroxyl radicals follow in the spectral record, their characteristic absorption at 0. 31 micrometers, marking the photodissociation of water molecules by solar ultraviolet radiation. These OH fragments form when water vapor encounters the Sun's energetic photons, breaking apart into component atoms that absorb light at specific wavelengths determined by quantum mechanical selection rules. The presence of hydroxyl signatures confirms that water sublimation occurs at rates approaching several hundred kilograms per hour, a molecular hemorrhaging that should drain any reasonable ice reserves within months. Carbon monoxide lines emerge in the near-infrared spectrum around 2.3 micrometers. Speaking of even more volatile materials escaping from the visitor's interior, these CO molecules require minimal solar heating to achieve gas phase, yet their abundance suggests reserves that exceed what surface deposits could provide. The spectral line profiles show Doppler broadening that indicates expansion velocities near 400 meters per second speeds that carry the escaping molecules well beyond the object's gravitational influence into the interplanetary medium. The molecular signatures display temporal variations that correlate with the visitor's rotational period, suggesting that outgassing occurs preferentially from specific surface regions. As 3i Atlas rotates, bringing different hemispheres into view, the spectral line strengths vary by factors of 2 or 3. This rotational modulation implies either compositional heterogeneity across the surface or geometric effects that concentrate molecular outflow in particular directions. The patterns repeat with clockwork precision every 8.7 hours, yet the phase relationships drift slowly over weeks of observation. Sodium D lines appear sporadically in high-resolution spectra taken when atmospheric conditions permit wavelength measurements accurate to parts per million. These atomic signatures at 589.0 and 589. 6 nanometers indicate the presence of metallic sodium in the escaping gas cloud, a component that suggests thermal processing of rocky materials at temperatures approaching 1000 Kelvin. Yet thermal models predict surface temperatures no higher than 200 Kelvin at the visitor's current solar distance, creating another impossible requirement for heat sources that remain unidentified. The spectroscopic measurements reveal isotopic ratios that differ significantly from solar system norms. Deuterium to hydrogen ratios in the water vapor appear enhanced by factors of 2 compared to terrestrial oceans, suggesting formation processes in interstellar environments where different nucleosynthetic pathways operate. These isotopic signatures carry the chemical fingerprints of stellar formation regions, unlike those that created our own solar system. Speaking of origins in galactic neighborhoods, where different physical conditions governed planetary accretion, carbon isotope ratios show similar anomalies, with carbon-13 abundances that exceed solar system values by measurable margins. These isotopic variations indicate that the carbon-bearing molecules escaping from 3A Atlas formed in stellar environments with neutron flux densities or temperature profiles that differ from those experienced by solar system materials during their initial condensation 4.5 billion years ago. The visitor carries within its molecular inventory the chemical signature of alien star formation processes. Organic spectral features appear intermittently in mid-infrared observations conducted during periods of exceptional atmospheric stability. Absorption bands near 3.4 micrometers suggest the presence of hydrocarbon molecules, possibly complex organic compounds that survive the visitor's journey through interstellar space, where cosmic ray bombardment should destroy such fragile chemical structures. The organic signatures remain weak and difficult to confirm, appearing at the limits of instrumental sensitivity like whispers from chemistry that operated under conditions unknown to terrestrial science. The Doppler shifts of spectral lines reveal the three-dimensional structure of the molecular outflow around 3I Atlas. Gas escaping from the sunward hemisphere shows blue-shifted absorption lines, indicating motion toward Earth as molecules accelerate away from the visitor's surface. The anti-solar hemisphere produces red-shifted signatures as escaping material moves away from terrestrial observers. These velocity patterns create a map of molecular motion that extends the visitor's effective size from its solid nucleus to a diffuse atmosphere spanning thousands of kilometers. High-resolution spectroscopy reveals fine structure in the molecular absorption lines that speaks of rotational and vibrational excitation, states within the escaping gas. The population distributions among different energy levels indicate gas temperatures near 150 Kelvin, significantly warmer than the equilibrium temperature expected for molecules in interplanetary space. This thermal excess suggests that the escaping gas carries energy from internal heating processes or receives warming from sources other than direct solar illumination. Some spectral observations detect polarization signatures in scattered sunlight that indicate the presence of microscopic dust particles mixed with the molecular outflow. These polarization measurements suggest grain sizes in the micrometer range larger than typical interstellar dust, but smaller than particles expected from mechanical erosion of rocky surfaces. The dust production implies either sublimation-driven fragmentation of surface materials or the entrainment of pre-existing particles within the escaping gas flow. Temporal monitoring reveals that spectral line strengths vary on multiple timescales beyond the primary rotational period. Some molecular signatures show enhancements that last several hours, suggesting localized outgassing events or the activation of specific surface regions. Other variations occur over periods of days or weeks, implying evolutionary processes that alter the visitor's outgassing behavior as it approaches our Sun along its hyperbolic trajectory. The accumulated spectroscopic data creates a portrait of an object that operates according to physical processes unknown in solar system science. Each molecular signature adds evidence for chemical and thermal behavior that violates established theories of how small bodies should respond to solar heating. The visitor's spectrum carries information encoded in wavelengths that speak of origins in stellar systems where different formation processes created materials with properties that challenge terrestrial understanding. In spectroscopy laboratories around the world, researchers compare the 3I Atlas observations with databases containing hundreds of thousands of reference spectra from meteorites, comets, and asteroids. The visitor's molecular fingerprints match no known classification, instead requiring the creation of entirely new categories for objects that bridge the gap between interstellar chemistry and planetary science. The starlight filtered through 3I Atlas whispers of processes that extend beyond current scientific knowledge, carrying within its spectral signatures questions that may outlast the instruments attempting to decode them. The astrometric measurements arrive with the precision of atomic clocks, each data point marking 3I Atlas's position against the stellar background with accuracies measured in milliarc seconds. This positional astronomy, the ancient science of tracking celestial motion, now operates at technological limits that would have seemed impossible just decades ago. Satellite-based telescopes eliminate atmospheric turbulence, while ground-based interferometers combine light from multiple apertures to achieve angular resolutions that can distinguish features smaller than coins viewed from thousands of kilometers away. Yet these exquisite measurements reveal motion that violates the fundamental principles of celestial mechanics. 3I Atlas accelerates along its trajectory in ways that pure gravitational theory cannot explain, displaying systematic deviations from Keplerian orbital motion that accumulate over weeks of observation. The visitor moves faster than calculations predict, as if invisible forces supplement the sun's gravitational attraction with additional acceleration directed along the object's velocity vector. The magnitude of this non-gravitational acceleration measures approximately 8 x 10⁻⁶ meters per second, squared, a seemingly negligible value that represents roughly 1/10 of Earth's surface gravity. Yet this minute force, applied continuously over the months of the visitor's passage through our solar system, produces cumulative positional changes that exceed measurement uncertainties by factors of 10 or more. The effect manifests as a systematic leading of the object's predicted position, as if 3I Atlas runs slightly ahead of schedule in its appointment with perihelion. This acceleration resembles the non-gravitational forces observed in comets, where sublimating ice creates reaction jets that can significantly alter orbital motion. The rocket effect occurs when molecules escaping from a comet's surface carry away momentum, creating thrust that supplements or opposes the gravitational forces governing the nucleus's trajectory. But 3 Atlas displays this acceleration at distances from the Sun where comet nuclei typically remain frozen into inactivity, where solar heating should be insufficient to drive significant sublimation of water ice or other common volatiles. The acceleration vector analysis reveals the forces act primarily in the radial direction away from the Sun, with smaller components along the orbital velocity vector. This geometry suggests that whatever process drives the acceleration operates most efficiently on the visitor's sunward hemisphere, where solar illumination reaches maximum intensity. Yet thermal calculations indicate that even at maximum solar heating, surface temperatures should remain below the sublimation threshold for water ice, the most abundant volatile compound expected in objects formed beyond the solar system's snowline. Sophisticated orbital fitting procedures attempt to reconcile the observed motion with theoretical predictions by introducing additional force terms into the equations of motion. These models treat the non-gravitational acceleration as a parameter to be determined from the astrometric data, allowing the mathematical framework to accommodate forces beyond pure gravity. The best fit solutions require accelerations that vary with distance from the Sun according to power laws that don't match any known physical process. The temporal evolution of the acceleration presents another puzzle that challenges conventional understanding. Rather than remaining constant or varying smoothly with solar distance, the non-gravitational forces display fluctuations that occur on timescales of days to weeks. These variations correlate weakly with the visitor's rotational period, suggesting connections between the acceleration magnitude and which hemisphere faces toward the Sun. Yet the correlations remain imperfect, as if additional factors influence the force generation beyond simple geometric considerations. Some acceleration episodes appear to occur independently of the visitor's orientation relative to the Sun, implying either internal energy sources or interactions with the solar wind that operate according to unknown physical principles. These episodes manifest as brief periods of enhanced acceleration that last several days before returning to baseline levels. The trigger mechanisms for these events remain unidentified, occurring without obvious correlation to solar activity, magnetic field changes, or other measurable environmental factors. The precision astrometry also reveals that 3I Atlas experiences torques that alter its rotational state over observable timescales. The visitor's spin period varies by small but measurable amounts, sometimes shortening by minutes per rotation cycle before gradually returning toward baseline values. These rotational changes suggest that whatever forces accelerate the object's center of mass also apply torques that modify its angular momentum in ways that solid body mechanics cannot explain. Gravitational modeling attempts to account for the acceleration by invoking previously unknown solar system mass concentrations or modifications to general relativity in the weak field limit. These theoretical exercises explore whether dark matter distributions, modified Newtonian dynamics, or exotic gravitational effects might explain the observed motion without requiring non-gravitational forces. However, the required mass distributions or gravitational modifications would produce observable effects on other solar system objects that remain undetected despite decades of high-precision orbital monitoring. The possibility of systematic measurement errors receives careful investigation as teams of astronomers cross-check their astrometric reductions and calibration procedures. Independent observations from different telescopes and analysis pipelines confirm the reality of the anomalous acceleration, eliminating instrumental artifacts or data processing errors as potential explanations. The visitor's motion deviates from gravitational predictions with statistical significance that exceeds 20 standard deviations, a certainty level that leaves little room for measurement uncertainty. Radio interferometry provides additional confirmation of the acceleration through observations at wavelengths immune to optical atmospheric effects. Very long. Baseline interferometry arrays track 3I Atlas by detecting faint thermal emissions from its heated surface, achieving positional accuracies that rival or exceed optical measurements. These radio observations confirm the systematic positional deviations, providing independent verification that the acceleration represents real physical motion rather than observational artifact. The acceleration magnitude shows weak but measurable dependence on the visitor's heliocentric distance, following approximately an inverse square relationship similar to solar illumination intensity. This correlation suggests that solar energy input drives whatever process generates the non-gravitational forces, yet the required coupling efficiency between absorbed solar radiation and mechanical thrust exceeds theoretical predictions by orders of magnitude. The visitor converts solar energy into directed momentum with an efficiency that challenges fundamental principles of thermodynamics and radiation pressure physics. Attempts to model the acceleration using conventional outgassing physics require mass loss rates that would deplete any reasonable volatile reserves within months of solar approach. Yet spectroscopic observations detect molecular outflow rates several orders of magnitude smaller than those needed to explain the observed thrust. This discrepancy between required and observed outgassing creates another impossible requirement for physical processes that operate with efficiencies unknown in solar system science. The accumulated astrometric evidence paints a portrait of an object that moves according to forces beyond current scientific understanding. Each measurement adds precision to parameters that describe increasingly impossible motion, as if 3I Atlas operates according to physical laws that extend beyond terrestrial knowledge. The visitor accelerates through space with mechanical persistence, carrying within its trajectory questions about the fundamental nature of matter, motion, and the forces that govern objects traveling between the stars. The outgassing phenomenon unfolds like a slow chemical reaction occurring in the vacuum laboratory of space itself. Across multiple wavelengths and observational techniques, instruments detect the steady release of molecular species from 3I Atlas at solar distances where such activity should remain impossible. The sublimation models that successfully predict comet behavior break down completely when applied to this interstellar visitor, revealing gaps in scientific understanding that extend to the fundamental physics of phase transitions in low-temperature environments. Water vapor continues its escape at rates that thermal calculations cannot justify. Surface temperatures derived from infrared observations indicate maximum values near 180 Kelvin, approximately 93 degrees below the freezing point of water under terrestrial conditions. At such temperatures, water ice should remain locked in crystalline stability for geological timescales. Yet spectroscopic measurements detect molecular outflow rates approaching 200 kilograms per hour. This mass loss requires vapor pressures that exceed equilibrium predictions by factors of thousands, suggesting either exotic ice structures or heating mechanisms that remain unidentified. The sublimation occurs preferentially from specific surface regions that rotate into view with the visitor's 8.7-hour period. High-resolution spectroscopy reveals that water vapor production peaks when certain hemispheres face toward the Sun, creating rotational modulation in the outgassing rate that implies compositional heterogeneity across the object's surface. Yet thermal models indicate that even the Sun-facing hemisphere should receive insufficient energy to drive significant sublimation at the visitor's current heliocentric distance of 2.8 astronomical units. Carbon monoxide outgassing presents an even more perplexing thermodynamic problem. This highly volatile molecule sublimes at temperatures below 70 Kelvin under vacuum conditions, making it among the first species to vaporize as an object approaches our Sun. Yet 3I Atlas continues producing carbon monoxide at rates that require surface temperatures of at least 50 Kelvin values that solar heating alone cannot provide at distances beyond Mars orbit. The persistent CO emissions suggests either internal heat sources or chemical processes that release bound molecules through mechanisms unknown to laboratory chemistry. Hydroxyl radical production rates indicate photodissociation processes operating with efficiencies that challenge established photochemistry. Solar ultraviolet radiation breaks apart water molecules to produce OH fragments at rates determined by quantum mechanical cross-sections measured in terrestrial laboratories. Yet, the OH production around 3I Atlas exceeds predictions based on the observed water vapor abundance and the known UV flux at the visitor's solar distance. This overproduction requires either enhanced photodissociation rates or additional OH sources that operate according to unknown chemical pathways. The molecular outflow displays velocity distributions that violate simple kinetic theory expectations. Gas escaping from the visitor's surface shows Doppler line profiles indicating expansion speeds near 400 meters per second velocities that require effective temperatures exceeding 400 Kelvin for water vapor molecules. Yet infrared measurements indicate surface temperatures no higher than 180 Kelvin, creating another impossible requirement for thermal conditions that exist nowhere on the observed object. The high-velocity outflow suggests either hydrodynamic acceleration of escaping gas or heating processes that remain invisible to thermal imaging. Dust production accompanies the molecular outflow in ways that contradict established models of sublimation-driven particle entrainment. Polarimetric observations detect microscopic grains escaping from 3I Atlas at rates that imply either mechanical erosion of surface materials or the disaggregation of larger particles through unknown fragmentation processes. The dust-to-gas mass ratio exceeds values typical for solar system comets, suggesting either unusual surface composition or entrainment mechanisms that operate with enhanced efficiency. The outgassing pattern shows systematic variations that occur on timescales longer than the visitor's rotational period. Multi-week monitoring reveals episodes of enhanced molecular production that last several days before gradually declining to baseline levels. These outgassing events display no obvious correlation with solar activity, magnetic field variations, or other environmental factors that might trigger increased sublimation. The episodes appear to originate from internal processes that operate according to their own temporal rhythms. Some molecular species appear and disappear in the spectroscopic record with temporal patterns that suggest compositional stratification within the visitor's interior. Methane signatures emerge sporadically in infrared spectra, indicating the presence of this highly volatile compound in subsurface reservoirs that connect to the surface through pathways activated by unknown triggers. The methane releases occur independently of the water vapor outgassing, implying separate volatile reservoirs with different activation mechanisms. Isotopic measurements of the outgassing molecules reveal fractionation patterns that challenge conventional sublimation physics. Light isotopes of hydrogen and carbon appear preferentially enriched in the escaping gas compared to heavy isotopes, suggesting either kinetic fractionation during molecular escape or chemical processing that operates according to unknown selection mechanisms. The isotopic ratios drift slowly over weeks of observation, as if the outgassing process samples different chemical reservoirs or undergoes evolutionary changes that alter the molecular composition. The thermal balance calculations that successfully model asteroid heating fail completely when applied to 3I Atlas. The visitor absorbs solar energy at rates determined by its cross-sectional area and surface reflectivity, yet radiates heat at infrared wavelengths that implies effective temperatures significantly below thermal equilibrium predictions. This apparent violation of energy conservation suggests either heat storage in internal reservoirs or energy transport mechanisms that operate with efficiencies unknown in conventional thermal physics. Laboratory experiments attempting to reproduce the visitor's outgassing behavior under simulated space conditions fail to achieve similar molecular production rates. Vacuum chambers equipped with cryogenic cooling systems and solar simulators cannot replicate the combination of low surface temperatures and high sublimation rates observed in 3I Atlas. The experimental results consistently underpredict outgassing by factors of hundreds, indicating that terrestrial laboratory conditions cannot reproduce whatever processes operate within the interstellar visitor. Theoretical models invoke exotic ice structures, clathrate hydrates, amorphous solids, or metastable crystalline phases to explain enhanced sublimation at low temperatures. These unusual ice forms, created under the extreme conditions of interstellar space, might possess vapor pressures that exceed normal crystalline ice by significant factors. Yet, laboratory synthesis of such materials requires conditions of pressure and temperature that seem inconsistent with formation in the near vacuum of interstellar environments. The outgassing continues with mechanical persistence, as if 3E Atlas operates according to thermodynamic principles that extend beyond current scientific understanding. Each night's spectroscopic observations add new data points to molecular production curves that violate established theory while displaying internal consistency that suggests underlying physical law. The visitor hemorrhages material into space through processes that remain invisible to the most sophisticated theoretical frameworks humanity can construct. In research laboratories dedicated to astrochemistry and planetary science, teams of scientists attempt to reconcile the observed outgassing with fundamental principles of thermodynamics and phase transition physics. The accumulated data creates requirements for theoretical explanations that challenge basic assumptions about how matter behaves under the extreme conditions of interplanetary space. 3I Atlas outgasses with sublime indifference to scientific theory, carrying within its molecular emissions questions that extend to the foundations of chemistry and physics themselves. The size estimates dance through impossible values like quantum states superposed in measurement uncertainty. Each observational technique applied to 3i Atlas yields dimensional parameters that seem to describe different objects entirely, creating a portrait of an entity that simultaneously appears massive and minuscule, dense and ethereal, solid and diffuse. The accumulated data suggests either systematic failures in multiple independent measurement methods or physical properties that challenge fundamental assumptions about the nature of matter in interstellar space. Radar observations from the Arecibo Observatory and Goldstone Deep Space Communications Complex achieve range measurements accurate to within meters. Yet the returned signals carry information that defies conventional interpretation. The radar cross-section implies an object roughly 400 meters in its longest dimension, substantial enough to generate the observed brightness through reflected sunlight. Yet, the same radar echoes display characteristics typical of targets less than 100 meters across. As if electromagnetic waves interact with 3i Atlas through scattering processes unknown in planetary radar astronomy. Thermal infrared measurements compound the dimensional confusion by suggesting effective radiating areas that vary by factors of 3 depending on observational wavelength. Mid-infrared observations at 10 micrometers indicate a cross-sectional area consistent with an object approximately 200 meters in diameter, assuming surface emissivity values typical of rocky materials. Yet far-infrared measurements at 70 micrometers suggest radiating areas appropriate for objects exceeding 800 meters across dimensions that would make 3i Atlas among the largest interstellar objects ever detected. The thermal emission spectra reveal another layer of impossibility in the visitor's apparent size. Different wavelengths of infrared radiation sample different depths within heated surfaces, creating thermal emission spectra that encode information about subsurface temperature distributions. For 3i Atlas, these spectra indicate thermal inertia, values measures of how quickly surfaces respond to changing illumination that require either exotic material properties or geometric structures unlike any solar system object. Occultation timing measurements provide yet another estimate of the visitor's dimensions through observations of background stars that pass behind 3i Atlas during its motion across the sky. These rare geometric alignments allow precise determination of the object's projected size as starlight dims during the brief eclipse events. The occultation data suggest an object no more than 150 meters across in any direction, significantly smaller than radar observations indicate yet consistent with some thermal emission measurements. Photometric modeling attempts to reconcile these contradictory size estimates by invoking extreme geometric properties that would make 3i Atlas among the most elongated objects known to astronomy. The brightness variations observed as the visitor rotates require axial ratios exceeding 10 one-dimensions that would create a cigar-shaped object roughly 1,000 meters long and less than 100 meters wide. Such extreme elongation might explain some observational inconsistencies, yet it creates new problems related to structural stability and rotational dynamics. The rotation period measurements themselves display systematic variations that challenge the assumption of rigid body motion. Initial observations suggested a stable 8.7-hour period typical of small asteroids in rotational equilibrium. Yet, continued monitoring reveals period variations approaching 10%, as if the visitor's rotation rate changes in response to internal processes or external torques that remain unidentified. Rigid, solid bodies cannot alter their rotation periods without external intervention. Yet 3i Atlas displays rotational behavior typical of fluid systems or loose aggregates held together by weak gravitational attraction. Gravitational modeling provides another approach to estimating the visitor's mass and dimensions through analysis of its orbital perturbations on other solar system objects. However, 3I Atlas remains too small and distant to produce measurable gravitational effects on planets, asteroids, or spacecraft. The absence of detectable gravitational influence places upper limits on the visitor's mass that correspond to objects no more than a few billion tons, consistent with dimensions of several hundred meters for materials with densities typical of rocky asteroids. Yet the combination of estimated mass and observed brightness implies bulk densities that span an impossible range of values. If 3I Atlas possesses the dimensions suggested by radar observations, its density would approach that of solid rock or metal, reasonable for objects formed through accretion processes in protoplanetary disks. However, if the visitor's true size matches occultation measurements, the required density would exceed that of pure metals, demanding materials more compact than any substance known to exist in planetary environments. The spectroscopic observations add another constraint to dimensional estimates through analysis of molecular outgassing rates and surface composition. The observed water vapor production requires either large surface areas to provide sufficient sublimating ice or exotic sublimation processes that operate with enhanced efficiency. Standard comet models suggest that the observed outgassing rates require active surface areas approaching 10,000 square meters dimensions, consistent with objects several hundred meters across. Yet thermal observations indicate effective radiating areas significantly smaller than these sublimation requirements demand. Polarimetric measurements reveal scattering properties that further complicate size determination through their implications for surface structure and composition. Light reflected from 3I Atlas shows polarization signatures that vary with rotational phase, suggesting surface features with dimensions comparable to optical wavelengths. These microscopic surface textures create scattering properties that might significantly enhance reflected brightness, allowing smaller objects to appear more luminous than size estimates based on simple geometric reflection would predict. The accumulated observational evidence creates a measurement paradox, where multiple independent techniques yield systematically inconsistent results. Radar observations suggest dimensions approaching 400 meters. Thermal emissions indicate sizes ranging from 200 to 800 meters. Occultations imply objects smaller than 150 meters, while outgassing requirements demand surface areas appropriate for bodies several hundred meters across. Each measurement technique operates according to well-established physical principles, yet their combined results seem to describe an object that cannot exist within the framework of conventional physics. Some theoretical models attempt to resolve these contradictions by invoking unusual structural properties that might explain the apparent size variations. Highly porous materials with bulk density significantly lower than solid rock could reconcile some observational inconsistencies, yet such structures would be mechanically unstable under the thermal stresses experienced during solar approach. Alternatively, surface compositions with exotic optical properties might create reflection and emission characteristics unlike those observed in solar system materials. The dimensional measurements continue their quantum dance between incompatible values, as if 3I Atlas exists in a superposition of size states that collapse only momentarily during specific observations. Each new measurement adds precision to parameters that describe an increasingly impossible object, one that simultaneously satisfies and violates multiple independent observational constraints. The visitor's dimensions remain as elusive as the physical processes that govern its behavior, carrying within their measurement uncertainty questions about the fundamental nature of matter and the reliability of observational astronomy itself. In conference rooms where astronomers gather to discuss their findings, computer screens display size estimates that span orders of magnitude while claiming comparable levels of measurement precision. The accumulated data suggests either systematic failures across multiple observational techniques or the existence of objects with properties that extend beyond current scientific understanding. 3-Eye Atlas shrinks and grows with each measurement like a cosmic Cheshire cat, leaving behind only the persistent grin of observational data that refuses to converge toward consistent physical parameters. The rotation unfolds in chaotic beauty through sequences of brightness measurements that defy the mechanical predictability expected from solid celestial bodies. Each night, photometric systems record the systematic dimming and brightening of 3-Eye Atlas as different surface regions rotate into view, creating light curves that should display the clockwork regularity characteristic of objects in stable rotational states. Yet, the visitor's rotation evolves through complex patterns that suggest either structural instability or dynamic processes operating according to principles unknown in solar system mechanics. The initial period determination yielded a seemingly stable 8.7-hour rotation, typical for small asteroids that have achieved rotational equilibrium through billions of years of minor collisions and tidal interactions. This period places 3-Eye Atlas within the normal range of rotation rates for objects of its estimated size, neither spinning so rapidly as to risk centrifugal disruption, nor so slowly as to suggest significant internal damping. Yet continued observations reveal systematic deviations from this nominal period that accumulate over weeks of monitoring. The period variations manifest as phase drift in the brightness maxima and minima, as if the visitor's rotation accelerates and decelerates according to internal rhythms that remain invisible to external observation. Some rotation cycles complete in as little as 8.1 hours, while others require nearly 9.4 hours variations that would demand impossible changes in angular momentum for objects governed by conservation laws. The period changes occur gradually over timescales of days to weeks, following patterns that suggest either energy dissipation within the rotating body or external torques applied by unknown mechanisms. High-cadence photometry reveals additional complexity in the rotational state through detection of brightness variations that occur on timescales much shorter than the primary rotation period. These rapid fluctuations, lasting minutes to hours, appear and disappear unpredictably while displaying no obvious correlation with the visitor's orientation relative to the Sun. Some short-term variations suggest the presence of surface features that reflect light preferentially in specific directions, creating brightness spikes when geometric conditions align favorably for terrestrial observers. The light curve morphology itself evolves over the weeks of observation, displaying shape changes that challenge assumptions about stable surface properties. Initial brightness variations showed the symmetric patterns expected from elongated objects with uniform surface composition. Yet later observations reveal increasingly complex light curves with multiple peaks and asymmetric features. These morphological changes suggest either chemical alterations occurring on the visitor's surface or the exposure of previously hidden regions through fragmentation or thermal processing. Spectroscopic monitoring reveals that different molecular species display rotational modulation with phases that don't align perfectly with the optical brightness variations. Water vapor outgassing peaks approximately 30 minutes before maximum brightness, suggesting that the most active sublimation regions don't coincide exactly with the most reflective surface areas. This phase offset implies either compositional heterogeneity across the visitor's surface or thermal lag effects that create temporal delays between solar heating and molecular outflow. The rotational axis orientation appears to undergo systematic changes that manifest as gradual shifts in the light curve amplitude and shape. Precession of the rotation axis. A phenomenon observed in some solar system asteroids could explain these long-term variations, yet the timescales involved seem too short for gravitational torques from the Sun or other planets. The apparent axis migration suggests either internal mass redistributions or external forces that apply torques through mechanisms unknown in celestial mechanics. Polarimetric measurements reveal that the degree of linear polarization varies not only with rotational phase, but also with the visitor's changing distance from the Sun. This dual dependence suggests that surface scattering properties evolve as solar heating increases, possibly through sublimation-driven changes in surface texture or the activation of previously dormant materials. The polarization patterns display complexity that requires either extreme surface roughness or optical properties unlike those measured in meteorite samples. Radar observations detect echo characteristics that change systematically with the visitor's rotational state, yet the changes don't repeat precisely from one rotation cycle to the next. Some radar reflections suggest smooth surfaces with metallic properties, while others indicate rough terrain with dielectric constants typical of rocky materials. These variable radar signatures imply either surface heterogeneity on scales smaller than the radar resolution, or temporal changes in surface properties that occur faster than the rotation period. The rotation state analysis reveals another troubling inconsistency in the visitor's mechanical behavior. The brightness variations require significant elongation, perhaps 10:1 axial ratios, to explain the observed amplitude of photometric modulation. Yet objects with such extreme shapes should undergo complex rotational dynamics, tumbling chaotically rather than spinning about fixed axes. 3I Atlas displays neither the simple rotation expected from nearly spherical bodies nor the complex tumbling characteristic of highly elongated objects, instead occupying an intermediate dynamical state that theoretical models struggle to explain. Thermal infrared observations show that surface temperatures vary across the rotating body according to patterns that don't match simple solar illumination models. Some surface regions appear significantly warmer than solar heating alone can explain, while others remain cooler than the equilibrium temperature for their solar distance. These temperature anomalies rotate with the visitor's spin period, suggesting either internal heat sources that vary across the surface or unusual thermal conductivity properties that create non-uniform heat distributions. The rotational energy budget presents another impossible requirement for the visitor's observed behavior. The systematic period variations imply energy dissipation or input rates that exceed predictions based on known damping mechanisms by orders of magnitude. Tidal interactions with the Sun remain too weak to explain the observed period changes, while internal friction in solid bodies operates too slowly to produce variations on timescales of weeks. The visitor's rotation evolves according to energy transport processes that remain unidentified. Some observations suggest that 3I Atlas experiences brief episodes of rapid rotation changes that occur over periods of hours rather than the gradual evolution typical of most period variations. These sudden spin changes appear correlated with enhanced outgassing events, suggesting either momentum transfer from escaping molecules or structural alterations that modify the visitor's moment of inertia. Yet the required coupling efficiency between molecular outflow and rotational dynamics exceeds theoretical predictions by significant factors. The accumulated rotational data paints a portrait of an object that spins according to dynamics unknown in solar system mechanics. Each photometric measurement adds precision to parameters that describe increasingly impossible rotational behavior, as if 3I Atlas operates according to physical laws that extend beyond current understanding of rigid body motion. The visitor tumbles through space with mechanical persistence, carrying within its chaotic rotation questions about the fundamental nature of angular momentum conservation and the stability of matter under extreme conditions. In planetarium software and orbital dynamics laboratories, computer simulations attempt to reproduce the visitor's rotational behavior using conventional physics models enhanced with exotic material properties and environmental interactions. The simulations consistently fail to match observations, instead producing either stable rotation, inappropriate for the measured period variations, or complete structural disruption, incompatible with the visitor's continued existence. 3i Atlas rotates with sublime indifference to theoretical expectations, spinning through space according to principles that challenge the foundations of celestial mechanics itself. The isotopic signatures whisper of stellar nurseries that existed when our galaxy wore a younger face, their chemical fingerprints preserved in molecules escaping from 3i Atlas like ancient pollen released from cosmic amber. Each spectroscopic measurement reveals elemental ratios that differ systematically from solar system norms. Speaking of nucleosynthetic processes that operated under physical conditions unknown in our local stellar neighborhood, the visitor carries within its molecular inventory the chemical memory of star formation regions where different temperatures, pressures, and neutron flux densities govern the nuclear reactions that forge the building blocks of matter. Deuterium to hydrogen ratios in the escaping water vapor exceed terrestrial values by factors approaching 3, marking the highest deuterium enrichment ever detected in solar system materials. This isotopic enhancement suggests formation in molecular clouds, where temperatures remained below 30 Kelvin for extended periods, allowing deuterium fractionation reactions to proceed with efficiencies impossible in warmer environments. The deuterium signatures indicate that the water molecules now sublimating from 3i Atlas condensed from interstellar gas that experienced chemical processing in regions colder than the cosmic microwave background radiation itself. Carbon isotope measurements reveal similar anomalies that speak of nucleosynthesis in stellar environments, unlike our Sun's formation region. The carbon-13 to carbon-12 ratio appears enhanced by approximately 40% compared to solar system standards, suggesting either contamination from nearby supernovae or formation in molecular clouds, enriched with products from asymptotic giant branch stars. These carbon isotope signatures indicate that the interstellar visitor originated in galactic regions where stellar evolution had progressed further than in the molecular cloud that eventually collapsed to form our solar system. Nitrogen isotope ratios display the most dramatic deviations from solar values, with nitrogen-15 abundances that exceed terrestrial measurements by factors of 5 or more. This extreme isotopic fractionation requires either formation temperatures below 10 Kelvin or chemical processing in environments exposed to cosmic ray bombardment intensities far exceeding those experienced by solar system materials during their initial condensation. The nitrogen signatures suggest origins in the outer regions of molecular clouds, where shielding from stellar radiation allowed exotic chemical pathways to operate. Oxygen isotope measurements present a more complex picture that challenges simple interpretations of the visitor's formation environment. While oxygen-18 abundances remain close to solar values, oxygen-17 shows systematic depletion that implies processing through nuclear reactions typical of massive stellar interiors. This isotopic pattern suggests either contamination from Wolf-Rayet star winds or formation in molecular clouds that contained unusual abundances of refractory materials ejected from evolved stars. The oxygen signatures speak of chemical histories that extend across multiple stellar generations. Sulfur isotope ratios reveal mass-independent fractionation patterns similar to those observed in the earliest solar system materials, yet with enhancements that exceed even the most primitive meteorites. These non-mass-dependent isotopic effects require photochemical processing by ultraviolet radiation with spectral characteristics different from our current Sun, possibly in the vicinity of massive O or B-type stars whose intense radiation fields create chemical conditions impossible in solar-type stellar environments. The sulfur signatures indicate formation in regions where stellar radiation environments differed fundamentally from those that govern solar system chemistry. The isotopic measurements also reveal temporal variations that suggest the outgassing process, samples different chemical reservoirs within the visitor's interior. Early observations showed relatively modest isotopic anomalies, while later measurements reveal increasingly extreme departures from solar values. This isotopic evolution implies either compositional stratification within 3I Atlas or preferential release of isotopically anomalous materials as solar heating penetrates deeper into the object's structure. Rare isotope measurements push instrumental capabilities to their limits while revealing signatures that challenge fundamental assumptions about galactic chemical evolution. Measurements of silicon-30, magnesium-26, and aluminum-26 abundances indicate processing in environments with neutron flux densities that exceeded those in typical stellar interiors. These rare isotope signatures suggest either formation near neutron stars or exposure to cosmic ray bombardment in interstellar environments with particle densities far exceeding current galactic values. The isotopic data creates constraints on the visitor's formation timescale that seem inconsistent with standard models of molecular cloud chemistry. The observed fractionation patterns require processing times approaching several million years in molecular cloud environments. Yet such extended chemical evolution should homogenize isotopic ratios rather than creating the extreme signatures observed in 3I Atlas. The isotopic evidence suggests either formation mechanisms unknown in current astrochemical theory or preservation processes that maintained chemical disequilibrium over geological timescales. Laboratory attempts to reproduce the visitor's isotopic signatures under simulated interstellar conditions consistently fail to achieve similar fractionation levels. Vacuum chambers equipped with cryogenic cooling systems and cosmic ray simulators cannot replicate the combination of extreme temperatures and extended processing times apparently required to create the observed isotopic patterns. The experimental results consistently underpredict fractionation by factors of 10 or more, indicating that terrestrial laboratory conditions cannot reproduce the chemical environments that shaped 3I Atlas during its formation. Some isotopic measurements reveal signatures that appear to violate conservation laws governing nuclear processes under normal stellar conditions. Certain isotope ratios require neutron capture cross-sections that exceed measured laboratory values, while others demand stellar nucleosynthesis environments with neutron densities that would trigger runaway nuclear reactions in conventional stellar models. These impossible requirements suggest either exotic nuclear processes or formation in environments where standard nuclear physics operates under modified conditions. The isotopic complexity extends to noble gas measurements that reveal xenon and krypton ratios unlike any solar system materials. These inert gases provide particularly reliable traces of formation conditions because their chemical inertness prevents alteration through secondary processing. The noble gas signatures indicate exposure to cosmic ray spallation reactions in interstellar environments. Yet, the required exposure times exceed the visitor's likely age by orders of magnitude. The noble gas isotopes speak of chemical histories that seem to require impossible combinations of time, temperature, and radiation exposure. Correlation analysis reveals systematic relationships between different isotopic signatures that provide clues about the physical processes responsible for their creation. Elements that undergo similar nuclear reactions show correlated isotopic anomalies, while chemically related species display isotopic patterns that suggest fractionation through common mechanisms. These correlations create a portrait of chemical processing in stellar environments where multiple exotic processes operated simultaneously to create the unusual signatures observed in 3I Atlas. The accumulated isotopic evidence creates requirements for formation environments that challenge current understanding of stellar nucleosynthesis and interstellar chemistry. Each measurement adds precision to isotopic ratios that describe materials formed under physical conditions unknown in our local galactic neighborhood. The visitor's molecular inventory preserves chemical fingerprints from stellar formation processes that operated billions of years ago in regions of space where different physical laws may have governed the nuclear reactions that create the elements. In isotope geochemistry laboratories, equipped with the most sensitive mass spectrometers available to terrestrial science, researchers attempt to decode the nuclear archaeology preserved in molecules escaping from 3I Atlas. The isotopic signatures resist interpretation through conventional frameworks, instead requiring theoretical models that extend beyond established nucleosynthesis theory. The visitor carries within its chemical memory the nuclear fingerprints of stellar processes that challenge fundamental assumptions about how elements form and evolve in galactic environments. The density calculations descend into mathematical impossibility, like equations dividing by zero. Each attempt to reconcile the visitor's observed mass with its estimated volume produces values that violate fundamental principles governing the behavior of matter under normal physical conditions. The accumulated measurements suggest either systematic errors across multiple independent observational techniques or the existence of an object whose internal structure defies every theoretical framework developed to understand planetary materials and their organization in gravitational fields. Gravitational estimates of the visitor's mass rely on the subtle perturbations its presence might create in the trajectories of other solar system objects. Yet, 3I Atlas remains too small and distant to produce measurable gravitational effects on planets, major asteroids, or spacecraft. The absence of detectable gravitational influence places upper limits on the visitor's mass corresponding to roughly 5 billion tons of value consistent with rocky asteroids several hundred meters in diameter, as yet inconsistent with the extreme brightness variations that suggest much larger dimensions. Radar cross-section measurements imply a target with effective dimensions approaching 400 meters in length, assuming surface properties similar to metallic asteroids that efficiently reflect radio waves. If this radar-derived size accurately represents the visitor's physical dimensions, the constrained mass would yield bulk densities near 0.3 grams per cubic centimeter less dense than cork, requiring internal void fractions exceeding 80%. Such extreme porosity would create mechanical structures too fragile to survive the thermal stresses experienced during solar approach or the centrifugal forces generated by rotation. Thermal infrared observations compound the density paradox by suggesting effective radiating areas that vary dramatically with observational wavelength. Mid-infrared measurements indicate objects roughly 200 meters across, with assumed emissivities typical of rocky surfaces, while far-infrared observations suggest radiating areas appropriate for bodies exceeding 800 meters in diameter. These thermal size estimates, combined with gravitational mass constraints, yield density values ranging from 0.1 to 2.0 grams per cubic centimeter, a variation that spans the difference between aerogel and solid rock. The outgassing mass loss rate provides another approach to estimating the visitor's bulk properties through analysis of how long current molecular emission rates could be sustained. Spectroscopic measurements indicate water vapor production approaching 200 kilograms per hour, while carbon monoxide outflow suggests additional mass loss of roughly 50 kilograms per hour. If these rates represent depletion of finite volatile reserves, the visitor could sustain current outgassing for only several thousand years before exhausting its internal ice inventory, a timescale impossibly short for objects that have drifted through interstellar space for millions of years. Yet the sustained outgassing requires volatile reservoirs that would constitute significant fractions of the visitor's total mass. If 3I Atlas contains sufficient water and carbon monoxide ice To maintain current emission rates for even modest geological time scales, the volatile inventory alone would exceed the gravitational mass constraints by comfortable margins. The outgassing data suggests either impossible mass concentrations or replenishment mechanisms that operate according to unknown physical principles. Structural stability analysis reveals another layer of impossibility in the visitor's apparent density distribution. Objects with bulk densities below 0.5 grams per cubic centimeter require either exotic low-density materials or internal structures dominated by void space. Yet highly porous objects become mechanically unstable when subjected to thermal gradients that create differential expansion stresses. The temperature variations observed across 3I Atlas should produce structural failure in materials with the low densities implied by size and mass constraints. The rotation period measurements provide additional constraints on internal density distribution through their implications for mechanical stability under centrifugal stress. Objects rotating with periods near 8.7 hours experience centrifugal accelerations that approach significant fractions of their surface gravitational attraction. For objects with the low bulk densities implied by dimensional estimates, centrifugal forces would exceed gravitational binding and cause structural disruption within hours of achieving rapid rotation. Yet, 3I Atlas maintains stable rotation despite possessing apparent material properties that should preclude such mechanical coherence. Theoretical models invoke rubble pile structures, loose aggregations of smaller fragments held together by weak gravitational attraction, to explain low bulk densities while maintaining structural integrity. Such configurations allow void fractions approaching 50% while providing sufficient mechanical strength to survive moderate thermal and rotational stresses. Yet rubble pile models fail to explain the systematic outgassing patterns observed in 3I Atlas, which require coherent internal structure to channel volatile materials from subsurface reservoirs to surface emission regions. Some density calculations attempt to resolve observational inconsistencies by invoking materials with exotic properties unknown in terrestrial laboratories. Metallic foams, crystalline structures with designed void spaces, or metamaterials with engineered density distributions might reconcile size and mass measurements while providing sufficient mechanical strength for structural stability. Yet, such exotic materials require manufacturing processes that seem inconsistent with formation through natural accretion in protoplanetary environments or interstellar molecular clouds. The density problem extends to fundamental questions about the conservation of mass and energy during the visitor's formation and evolution. If 3I Atlas possesses the low bulk density implied by observational constraints, its gravitational binding energy would be insufficient to retain volatile materials against thermal escape over geological timescales. The visitor should have lost its inventory of water and carbon monoxide ices during millions of years of exposure to cosmic ray heating and background radiation in interstellar space. Alternative theoretical approaches invoke hollow structures or cavern systems within the visitor's interior to explain low bulk densities while maintaining sufficient structural integrity for mechanical stability. Natural processes such as impact excavation, thermal cycling, or chemical dissolution might create internal void spaces that reduce overall density without compromising structural coherence. Yet the formation of large internal cavities requires energy sources or chemical processes that remain unidentified in conventional planetary science. Comparative analysis with other interstellar objects provides little guidance for resolving the density paradox. Oumuamua displayed similar inconsistencies between estimated size and inferred mass, while 2I Borisov showed density values within normal ranges for cometary materials. The limited sample of confirmed interstellar visitors prevents statistical analysis of whether extreme density values represent common characteristics of objects formed in external stellar systems or unique properties specific to individual visitors. The density measurements resist convergence toward physically reasonable values, instead spanning ranges that encompass both the lightest aerogels and the densest rocky materials. Each observational technique contributes constraints that appear individually reasonable yet collectively impossible, creating a measurement paradox that challenges fundamental assumptions about matter, structure, and the reliability of astronomical observations themselves. The visitor's bulk properties remain as elusive as the forces that govern its motion and the processes that drive its chemical activity. Laboratory simulations attempting to create materials with the extreme density values implied by 3A Atlas observations consistently fail to achieve stable configurations. High porosity materials collapse under their own gravitational attraction or fragment under thermal stress, while low-density synthetic materials lack the mechanical properties necessary for astronomical scale objects. The experimental results suggest that the visitor's apparent density values represent either measurement artifacts or material properties that extend beyond current scientific understanding. In materials science laboratories and theoretical physics departments, researchers construct mathematical models that attempt to accommodate the visitor's impossible density constraints. The calculations require either violations of established physical law or the existence of matter with properties unknown in terrestrial science. 3I Atlas drifts through space with sublime indifference to density measurements, carrying within its structure questions that extend to the fundamental nature of matter, mass, and the organization of atoms in gravitational fields. The magnetic field measurements flicker through data streams like aurora dancing across digital skies, revealing electromagnetic signatures that have never been detected around any solar system object. Magnetometer readings from spacecraft positioned throughout the inner solar system detect field fluctuations that correlate precisely with 3I Atlas's changing brightness, creating temporal patterns that suggest electromagnetic processes operating according to principles unknown in planetary magnetism. The visitor generates magnetic phenomena that challenge fundamental assumptions about how small bodies interact with the solar wind and interplanetary magnetic environment. The baseline interplanetary magnetic field strength near Earth's orbit measures approximately 5 nanotesla, a vanishingly weak value that represents the stretched and diluted remnant of our Sun's magnetic field carried outward by the solar wind. Yet magnetometer stations detect systematic variations in this background field that occur with the same 8-7-hour period as the visitor's rotation, suggesting that 3 Atlas somehow influences magnetic conditions across distances spanning millions of kilometers. The magnetic perturbations appear far too large for an object of the visitor's estimated size, requiring either electromagnetic amplification mechanisms or field generation processes that operate with impossible efficiency. The magnetic variations display complex waveforms that resist interpretation through conventional magnetospheric physics. Simple dipole field models. The theoretical framework successfully applied to planetary magnetic fields fail completely when fitted to the 3I Atlas observations. Instead, the detected signatures suggest multipole field configurations with temporal variations that require either rapid changes in internal current distributions or interactions with the solar wind that operate according to unknown electromagnetic principles. Spectropolarimetric observations reveal that light reflected from 3I Atlas carries magnetic field signatures encoded in Zeeman splitting of atomic absorption lines. These spectroscopic measurements detect surface magnetic field strengths approaching several thousand nanotesla values that exceed typical asteroid magnetic fields by orders of magnitude. The spectroscopic field measurements vary systematically with the visitor's rotational phase, suggesting either magnetic field configurations that change as different surface regions rotate into view, or electromagnetic induction effects that respond to varying solar wind conditions. The correlation between magnetic field variations and brightness changes suggests electromagnetic processes that somehow influence the visitor's optical properties. As magnetic field strength increases, measured through both remote sensing and in situ magnetometer readings, the visitor's reflected light intensity shows corresponding enhancements that occur with temporal precision measured in minutes. This electromagnetic optical coupling requires either magneto-optical effects unknown in conventional materials or surface processes that respond directly to magnetic field variations. Solar wind plasma measurements detect particle acceleration events that coincide precisely with periods of enhanced magnetic activity around 3I Atlas. During these episodes, charged particle detectors record proton and electron energies that exceed background solar wind values by factors of 10 or more. The particle acceleration occurs preferentially during magnetic field enhancements, suggesting either magnetic reconnection processes or electromagnetic induction phenomena that operate with efficiencies unknown in space physics. The magnetic field configuration around 3I Atlas appears to create localized disturbances in the solar wind flow pattern that extend far beyond the visitor's physical dimensions. Plasma wave detectors identify shock structures and magnetic field discontinuities that propagate outward from the visitor's vicinity at velocities approaching the solar wind speed. These electromagnetic disturbances carry energy densities that exceed those expected for objects of 3I Atlas's estimated mass, suggesting either efficient coupling between the visitor and solar wind plasma or electromagnetic field generation mechanisms that operate independently of gravitational effects. Radio astronomy observations detect electromagnetic emissions from 3I Atlas at frequencies ranging from several megahertz to multiple gigahertz, creating a broadband emission spectrum unlike any previously observed from asteroids or comets. The radio emissions display systematic variations that correlate with both the visitor's rotation period and the strength of detected magnetic field fluctuations. Some emission frequencies show polarization characteristics that indicate synchrotron radiation from relativistic charged particles, a phenomenon typically associated with pulsars, black holes, or other exotic astrophysical objects rather than small solar system bodies. The temporal evolution of magnetic activity reveals systematic changes that occur over timescales much longer than the visitor's rotation period. Multi-week monitoring shows gradual increases in baseline magnetic field strength accompanied by corresponding enhancements in electromagnetic emission intensity. These long-term changes suggest either internal magnetic dynamo processes or systematic modifications in the visitor's electromagnetic environment as it approaches our Sun along its hyperbolic trajectory. Laboratory measurements of meteorite samples reveal magnetic field strengths that rarely exceed several hundred nanotesla, even in materials containing significant iron-nickel alloy concentrations. The magnetic fields detected around 3I Atlas exceed these meteoritic values by factors of 10, requiring either exotic magnetic materials or electromagnetic induction processes that operate with efficiencies unknown in planetary science. Theoretical models invoking superconducting materials or ferromagnetic substances with unusual properties fail to explain the observed field strengths while maintaining consistency with other observational constraints. The magnetic field geometry, inferred from multiple measurement techniques, suggests configurations that violate fundamental principles of electromagnetic field theory. Maxwell's equations require that magnetic field lines form closed loops without beginning or ending. Yet the field patterns around 3I Atlas appear to contain monopole-like configurations that should be impossible under normal physical conditions. These apparent violations of electromagnetic field theory create mathematical inconsistencies that challenge basic assumptions about the nature of magnetism itself. Plasma physics simulations attempting to model the electromagnetic environment around 3I Atlas consistently fail to reproduce the observed magnetic field signatures. Computer codes that successfully predict magnetospheric behavior around planets and comets produce either field configurations too weak to match observations or electromagnetic instabilities that would rapidly dissipate the detected field strengths. The visitor's magnetic properties resist theoretical modeling through conventional plasma physics frameworks, requiring either exotic material properties or electromagnetic processes that extend beyond current scientific understanding. Some magnetic field measurements suggest periodic reversals in field polarity that occur over timescales of several hours, much faster than geomagnetic reversals on Earth, which require thousands of years for completion. These rapid polarity changes imply either internal magnetic dynamo processes that operate with impossible efficiency or interactions with external electromagnetic fields that somehow trigger systematic magnetic reconfigurations. The polarity reversal events coincide with enhanced particle acceleration and radio emission episodes, suggesting electromagnetic processes that remain coupled through unknown mechanisms. The accumulated magnetic field data creates requirements for theoretical explanations that challenge fundamental principles of electromagnetism and plasma physics. Each magnetometer reading adds precision to field strength measurements that exceed all known mechanisms for magnetic field generation in small astronomical objects. The visitor carries within its electromagnetic signatures questions about the nature of magnetism, the behavior of charged particles in space, and the fundamental relationship between matter and electromagnetic fields. In plasma physics laboratories and theoretical electromagnetism departments, researchers construct mathematical models attempting to accommodate the impossible magnetic field measurements detected around 3I Atlas. The calculations require either violations of Maxwell's equations or the existence of materials with electromagnetic properties unknown to terrestrial science. The visitor drifts through space, generating magnetic phenomena with sublime indifference to theoretical constraints, carrying within its electromagnetic activity processes that challenge the foundations of field theory itself. The trajectory calculations extend into the future with mathematical certainty that transforms wonder into melancholy, revealing that 3I Atlas will depart our solar system forever along a hyperbolic path that carries no possibility of return. The orbital mechanics speak with the cold precision of differential equations, describing motion governed by conservation laws that permit no exceptions for human curiosity or scientific desire. In approximately 18 months, the visitor will cross Neptune's orbital distance while accelerating toward interstellar space at velocities that increase steadily under our Sun's gravitational assistance. The departure geometry carries the visitor toward coordinates in the constellation Lynx, a faint stellar pattern visible from Earth's northern hemisphere during winter months. This destination represents no particular stellar system, merely a direction in three-dimensional space where background stars happen to align when viewed from our solar system's perspective. The visitor will spend millions of years traversing the space between stars, drifting through regions so empty that encounters with individual hydrogen atoms become rare events separated by kilometers of vacuum. Long-term orbital integration reveals that 3I Atlas will achieve escape velocity from our solar system with a hyperbolic excess speed approaching 11 kilometers per second, the velocity it will retain after climbing out of our Sun's gravitational potential. Well, this departure speed ensures that the visitor will never return, even if gravitational perturbations from passing stars alter its trajectory over geological timescales. The mathematics of orbital mechanics admit no ambiguity. This encounter represents humanity's first and final opportunity to study this particular interstellar wanderer. The visitor's closest approach to our Sun perihelion occurs at a heliocentric distance of 37 million kilometers, well inside Mercury's orbit but comfortably beyond the solar corona's superheated plasma. At this distance, solar radiation will heat the object's surface to temperatures exceeding 500 Kelvin, potentially triggering enhanced outgassing events that may briefly increase the visitor's brightness by several magnitudes. The perihelion passage represents the climactic moment of 3I Atlas's solar system encounter, after which it begins its inexorable recession toward interstellar darkness. Gravitational modeling indicates that our Sun's tidal forces will have negligible effects on the visitor's structural integrity during close approach, unlike comet nuclei that sometimes fragment when passing near our star. 3I Atlas appears mechanically robust enough to survive perihelion passage without catastrophic disruption. The visitor's mysterious structural properties, whatever they might be, seem adequate to maintain cohesion against tidal stresses that would challenge more conventional objects of comparable size. The departure trajectory also reveals that 3I Atlas will pass within several astronomical units of Jupiter approximately 6 months after perihelion, offering the giant planet's gravitational field one final opportunity to influence the visitor's motion. Yet, Jupiter's perturbations will prove insufficient to significantly alter the hyperbolic trajectory, instead providing only minor course corrections that change the departure direction by fractions of a degree. The visitor's kinetic energy exceeds Jupiter's gravitational binding by comfortable margins, ensuring that even the solar system's most massive planet cannot capture this interstellar wanderer. Observational planning calculations indicate that 3I Atlas will fade beyond the detection limits of Earth-based telescopes approximately 8 months after perihelion passage. The visitor's recession from our Sun will reduce reflected sunlight intensity according to inverse square law, while increasing distance from Earth further diminishes apparent brightness. Within 2 years of discovery, this cosmic stranger will disappear into the observational noise that masks countless distant objects too faint for current instrumentation to detect. The trajectory analysis also predicts optimal observation windows for different types of measurements during the visitor's remaining time within detection range. Spectroscopic observations will remain feasible for roughly 14 months, while high-resolution imaging requires the visitor to remain within Mars' orbital distance, a constraint that limits detailed surface studies to a narrow temporal window around perihelion passage. Each observational technique faces its own distance limitations that create a countdown toward the visitor's disappearance from human observation. Spacecraft mission studies reveal that no existing or planned space probe could intercept 3I Atlas before its departure from the solar system. The visitor's hyperbolic trajectory requires delta-V budgets that exceed the capabilities of chemical propulsion systems. While its discovery occurred too late to allow mission planning and spacecraft preparation, humanity must content itself with remote observations through Earth-based instruments, watching helplessly as this cosmic messenger recedes beyond our technological reach. The departure calculations extend beyond simple orbital mechanics to include relativistic effects that become significant at the high velocities achieved during solar system escape. As 3I Atlas accelerates away from our Sun, time dilation and length contraction effects will introduce corrections to classical trajectory predictions that amount to milliarc seconds per year in apparent position. These relativistic contributions remain far below current measurement precision, yet they remind observers that the visitor's motion approaches regimes where Einstein's theories modify the Newtonian mechanics that govern most astronomical objects. Future trajectory uncertainties arise from the non-gravitational accelerations that continue to influence the visitor's motion in unpredictable ways. The same mysterious forces that create systematic deviations from pure Keplerian orbits will continue operating during 3I Atlas's departure phase, potentially altering the final escape trajectory by measurable amounts. These uncertainties prevent precise prediction of the visitor's ultimate destination, instead defining probability distributions for its future location among the stars. Galactic dynamics calculations project the visitor's motion through three-dimensional stellar neighborhoods over timescales spanning millions of years. The analysis suggests that 3I Atlas will encounter stellar systems at distances ranging from several light-years to hundreds of light-years. Yet none of these future approaches will occur close enough to significantly alter the visitor's trajectory. The interstellar wanderer will drift through galactic space according to the gravitational potential of stellar populations, following paths that trace the galaxy's overall rotation and mass distribution. The psychological impact of the trajectory calculations weighs heavily on astronomers who have devoted months to studying this cosmic visitor. Each orbital computation confirms the inexorable nature of celestial mechanics, the indifference of gravitational forces to human desire for extended contact with interstellar objects. The visitor approaches, brightens, offers tantalizing glimpses of alien chemistry and physics, then recedes according to mathematical laws that admit no appeals for mercy or extended observation time. Statistical analysis suggests that similar interstellar visitors pass through our solar system every few years, yet most remain undetected due to their small size, high velocity, or unfavorable geometric circumstances. 3I Atlas represents a fortunate detection of phenomena that occur regularly but usually escape human notice. The visitor's departure returns our solar system to its normal state of isolation from interstellar objects, leaving behind only archived data and the knowledge that cosmic wanderers traverse the space between stars with frequency that exceeds previous estimates. The trajectory's mathematical certainty transforms scientific opportunity into temporal constraint, creating urgency that drives observational campaigns across multiple continents and wavelength ranges. Every clear night becomes precious as astronomers race against orbital mechanics to extract maximum scientific return from humanity's brief encounter with this interstellar messenger. The visitor's path through our solar system marks a countdown toward the resumption of cosmic solitude that has characterized human existence throughout recorded history. The laboratory chambers hum with mechanical persistence as teams of scientists across the globe attempt to recreate the impossible behaviors displayed by 3I Atlas under controlled terrestrial conditions. Vacuum systems evacuate test chambers to pressures that approach interplanetary space, while cryogenic refrigerators cool sample materials to temperatures that mimic the thermal environment of objects drifting between stars. Yet each experimental attempt produces results that fall orders of magnitude short of matching the visitor's observed properties, revealing fundamental gaps in scientific understanding that extend to the basic physics of matter under extreme conditions. The sublimation experiments begin with the most optimistic theoretical frameworks, using pure water ice samples cooled to temperatures matching infrared observations of 3I Atlas's surface. Solar simulators provide illumination intensities equivalent to those experienced by the visitor at its current heliocentric distance, while mass spectrometers monitor molecular outflow rates with sensitivities approaching single-molecule detection. The results consistently show sublimation rates 3 orders of magnitude lower than spectroscopic observations detect around the interstellar visitor, even when accounting for uncertainties in surface composition and geometric effects. Exotic ice structures become the focus of increasingly desperate theoretical speculation as researchers invoke clathrate hydrates, amorphous solids, and metastable crystalline phases to explain enhanced sublimation efficiency. Laboratory synthesis of these unusual ice forms requires pressures and temperatures that seem inconsistent with formation in interstellar environments. Yet experimenters create artificial samples that display vapor pressures exceeding normal crystalline ice by significant factors. Even these exotic materials fail to match the outgassing rates observed in 3I Atlas by comfortable margins, suggesting either measurement errors or physical processes unknown to terrestrial chemistry. Electromagnetic field experiments attempt to reproduce the magnetic signatures detected around the visitor through laboratory simulations using superconducting coils, ferromagnetic materials, and plasma confinement systems. High field magnets generate magnetic flux densities that exceed Earth's geomagnetic field by factors of thousands, while particle accelerators create charged particle beams that simulate solar wind conditions. The laboratory magnetic fields remain stable and predictable, displaying none of the systematic variations or impossible field geometries that characterize the electromagnetic environment around 3I Atlas. Rotation dynamics laboratories construct mechanical simulators designed to reproduce the visitor's chaotic spin behavior using objects with various internal structures and material properties. Rubble pile configurations, fluid-filled containers, and composite materials with engineered density distributions undergo rotation testing in vacuum chambers that eliminate air resistance effects. The mechanical systems either maintain stable rotation periods that violate the observed period variations or fragment catastrophically under centrifugal stress, failing to achieve the intermediate dynamical state that 3I Atlas somehow maintains. Thermal modeling experiments use infrared heating systems to simulate solar illumination while monitoring surface temperature distributions through high-resolution thermal imaging. Test objects with various geometric configurations and surface compositions undergo heating cycles that reproduce the thermal environment experienced by 3I Atlas during its approach to perihelion. The laboratory measurements consistently show temperature distributions that match theoretical predictions based on thermal conductivity and surface emissivity, displaying none of the anomalous heat patterns that characterize the visitor's thermal emission. Optical scattering experiments attempt to explain the visitor's unusual brightness variations and polarization properties through laboratory measurements using particles with different shapes, compositions, and surface textures. Light scattering chambers equipped with tunable laser sources illuminate sample materials, while polarimeters measure reflected light characteristics from multiple viewing angles. The laboratory results consistently produce scattering patterns that follow established theory for electromagnetic wave interactions with matter, showing none of the systematic deviations that make 3I Atlas's optical properties unique. Isotopic fractionation experiments seek to recreate the extreme isotope ratios detected in molecules escaping from the visitor through simulated interstellar chemistry processes. Ultra-high vacuum chambers equipped with cosmic ray simulators and cryogenic cooling systems attempt to reproduce the chemical environments where the visitor presumably formed billions of years ago. The experiments consistently produce isotopic fractionation levels that remain several orders of magnitude below the extreme values measured in 3I Atlas's molecular emissions, even after processing times that exceed practical laboratory constraints. Density measurement experiments attempt to create materials with the impossible bulk density values implied by the visitor's observational characteristics through various manufacturing techniques including aerogel synthesis, foam metal production, and controlled porosity ceramics. The laboratory materials either collapse under gravitational stress when scaled to astronomical dimensions or display mechanical properties incompatible with the structural stability requirements for objects rotating at the periods observed in 3I Atlas. Acceleration experiments use ion propulsion systems, photon pressure devices, and chemical thrusters to reproduce the non-gravitational forces that influence the visitor's orbital motion. Theoretical calculations indicate the thrust requirements for matching the observed accelerations, yet experimental systems operating at maximum efficiency produce forces that fall short of the required values by factors of hundreds. The laboratory propulsion experiments suggest either measurement errors in the astronomical observations or thrust generation mechanisms that operate according to unknown physical principles. Spectroscopic laboratories attempt to reproduce the visitor's unusual molecular emission signatures through controlled sublimation of various chemical compounds under simulated space conditions. High-resolution spectrometers monitor molecular outflow from heated samples while comparing line strengths, Doppler shifts, and temporal variations with observations of 3I Atlas. The laboratory spectra consistently show molecular production rates and velocity distributions that match theoretical predictions based on thermal equilibrium, displaying none of the systematic anomalies that characterize the visitor's spectroscopic behavior. Computational modeling laboratories construct three-dimensional simulations that combine multiple physical processes in attempts to reproduce the visitor's complex behavior through numerical calculations. The simulations incorporate gravity, thermodynamics, electromagnetic theory, and chemical kinetics using the most sophisticated algorithms available to computational physics. The computer models consistently produce either stable configurations incompatible with observed variations or unstable systems that undergo rapid disruption, failing to achieve the delicate balance of properties that somehow characterizes 3I Atlas. Collaborative research networks coordinate experiments across multiple institutions in attempts to identify systematic errors or overlooked physical processes that might explain the discrepancies between laboratory results and astronomical observations. International teams share data, cross-check measurement techniques, and compare results using identical experimental protocols. The collaborative efforts consistently confirm that terrestrial laboratory conditions cannot reproduce the combination of properties observed in the interstellar visitor, suggesting either fundamental limitations in experimental capabilities or the operation of physical processes unknown to current science. The accumulated experimental failures create a portrait of scientific inadequacy that extends across multiple disciplines from chemistry and physics to materials science and engineering. Each laboratory measurement adds precision to discrepancies that grow larger rather than smaller as experimental techniques improve and theoretical models become more sophisticated. The visitor's properties resist terrestrial reproduction with sublime indifference to human efforts. As if 3I Atlas operates according to physical laws that extend beyond the reach of Earth-based scientific investigation, in research institutions around the world, teams of scientists gather around experimental apparatus that consistently fails to match astronomical observations, forced to confront the possibility that their understanding of matter, energy, and the fundamental forces that govern physical processes remains incomplete. The visitor drifts through our solar system according to principles that terrestrial science cannot recreate, carrying within its mysterious behavior questions that challenge the foundations of physics itself. The silence deepens like winter settling over a sleeping landscape as 3I Atlas recedes past Mars' orbital distance, carrying its secrets toward the constellation Lynx with mechanical indifference to humanity's desperate observations. Each night brings fainter photometric measurements as the visitor's angular distance from the Sun decreases the illuminated cross-section visible from Earth, while simultaneously the increasing range dilutes reflected sunlight according to inverse square laws that operate with mathematical brutality. The brightness that once challenged telescopic detection limits now approaches the threshold where signal disappears into the random noise that characterizes astronomical observations at the edge of instrumental capability. The molecular outgassing that defines so much of the visitor's mysterious behavior begins its own recession into undetectability as spectroscopic measurements strain against sensitivity limits, determined by photon counting statistics and atmospheric turbulence. Water vapor absorption. Lines that once appeared clearly in high-resolution spectra now require integration times measured in hours rather than minutes. While the hydroxyl radical signatures fade into the wavelength regions where Earth's atmospheric absorption creates systematic uncertainties that exceed the strength of astronomical signals. The carbon monoxide emissions become intermittent detections subject to debate about their statistical significance versus instrumental artifacts. Yet, the non-gravitational acceleration continues with stubborn persistence even as the visitor fades beyond detailed observation. Astrometric measurements of sufficient precision to detect positional deviations from pure Keplerian motion require longer observational baselines, as the angular motion across the sky slows with increasing distance from Earth. The systematic leading of predicted positions that characterizes the visitor's anomalous acceleration accumulates over weeks and months of observation, creating positional errors that exceed measurement uncertainties by factors that increase steadily with time. Whatever forces drive this impossible acceleration operate according to their own physical logic, indifferent to human attempts at measurement or understanding. The rotational period measurements become increasingly uncertain as photometric variations diminish below reliable detection thresholds. The brightness modulation that once provided clear evidence for 8.7-hour rotation periods now competes with systematic errors in photometric calibration and random variations in atmospheric transmission. Some observations suggest that the period variations continue as the visitor recedes, while others indicate either stable rotation or complete cessation of detectable periodic behavior. The rotational state of 3I Atlas dissolves into observational uncertainty like details fading in twilight. Thermal infrared observations face their own recession into undetectability as the visitor's radiated heat becomes indistinguishable from background emission sources that include zodiacal dust, distant galaxies, and instrumental thermal noise. The temperature anomalies that once suggested exotic thermal properties or internal heat sources fade into the measurement uncertainties that characterize infrared astronomy at the limits of technological capability. The thermal emission spectrum that provided clues about surface composition and energy balance becomes a series of upper limits rather than positive detections. Magnetic field measurements experience perhaps the most dramatic decline in signal strength as the electromagnetic effects that once perturbed interplanetary space conditions fade below the noise level of magnetometer instruments designed to measure much stronger planetary magnetic fields. The systematic variations that correlated with the visitor's rotational period and brightness changes disappear into the irregular fluctuations that characterize the solar wind's interaction with Earth's magnetosphere. The impossible magnetic phenomena that challenged electromagnetic theory fade into observational memory rather than ongoing measurement. Radio astronomy observations detect increasingly sparse emissions as the broadband electromagnetic spectrum that once extended from megahertz to gigahertz frequencies contracts into narrow bands that require longer integration times to achieve statistical significance above background noise. The polarization characteristics that suggested synchrotron radiation from relativistic particles become marginal detections subject to systematic uncertainties introduced by Earth's ionospheric variability and interference from terrestrial radio sources. The electromagnetic signature of 3I Atlas recedes into the confusion of radio frequency emission that characterizes the modern technological environment. Spectropolarimetric measurements that once revealed magnetic field strengths and surface scattering properties through Zeeman, splitting of atomic absorption lines, now require telescope time allocations measured in entire nights rather than hours to achieve marginal detections. The polarization signals that indicated impossible magnetic phenomena fade into the systematic uncertainties that plague polarimetric astronomy, when observing faint sources near the detection threshold. The visitor's optical properties become matters of theoretical speculation rather than observational determination. International observational campaigns coordinate telescope schedules across multiple continents in desperate attempts to maximize photon collection efficiency before the visitor fades beyond recovery. Professional observatories reserve their most sensitive instruments for 3-eye atlas observations, while amateur astronomers contribute measurements from smaller telescopes that aggregate into databases providing statistical confirmation of systematic trends. Yet even these collaborative efforts face the inexorable mathematics of observational astronomy. Signals decrease with distance while noise remains constant, creating signal-to-noise ratios that approach unity and then decline beyond reliable measurement thresholds. The scientific literature begins its own transformation as research papers shift from reporting positive detections to establishing upper limits on various physical parameters. Conference presentations evolve from descriptions of impossible observations to statistical analyses of measurement uncertainties and systematic error sources. The visitor's extraordinary properties become historical curiosities rather than ongoing research targets, preserved in archived data rather than fresh observations that could resolve fundamental questions about interstellar object physics. Database archival efforts race against time to preserve all accumulated measurements before the visitor disappears beyond recovery, creating digital repositories that will outlast the observations they contain. Spectroscopic atlases, photometric light curves, astrometric position measurements, and thermal emission data undergo careful calibration and documentation for future researchers who may develop theoretical frameworks capable of explaining the impossible behaviors observed in 3-eye atlas. The scientific value of these archived observations may increase over time as understanding advances, yet the opportunity for additional measurements recedes according to orbital mechanics that admit no appeals for extended observation time. Theoretical modeling efforts intensify even as observational capabilities decline, attempting to extract maximum scientific understanding from the accumulated data before additional observations become impossible. Computer simulations incorporate all available measurements while exploring parameter spaces that might reconcile contradictory observations through exotic physics or measurement systematic errors. Yet the theoretical models consistently fail to reproduce the full range of observed phenomena, instead explaining individual characteristics while remaining unable to account for the visitor's complete behavioral profile. The visitor's recession creates a psychological transition for the astronomical community as researchers confront the finite nature of this cosmic encounter. The excitement of discovering impossible physics gives way to melancholy recognition that humanity's first detailed study of an interstellar visitor approaches its conclusion according to celestial mechanics that operate with indifference to scientific curiosity. Each observational session might represent the final opportunity to detect specific phenomena, creating urgency that drives around-the-clock observing campaigns despite declining signal strength. The silence that approaches carries within it the weight of unanswered questions that may persist for decades or centuries before similar interstellar visitors provide opportunities for renewed investigation. 3-eye atlas recedes toward interstellar darkness, carrying secrets about matter, energy, and fundamental physics that terrestrial science proved unable to decode during humanity's brief opportunity for detailed study. The visitor's acceleration continues with mechanical persistence while its electromagnetic, thermal, and chemical signatures fade into the observational noise that will eventually erase all trace of its passage through our solar system. The legacy crystallizes in digital archives that will outlast the civilizations that created them, preserving humanity's first detailed encounter with an interstellar visitor in databases scattered across continents and backup systems designed to survive technological collapse. The accumulated measurements of 3Y atlas spectroscopic atlases, photometric light curves, astrometric coordinates, thermal emission data represent the most comprehensive observational record ever compiled for an object whose physical properties violate established scientific theory. These data files contain questions encoded in wavelengths and numbers, mathematical puzzles that future generations may solve using theoretical frameworks not yet imagined. The visitor fades below detection thresholds with the inevitability of sunset, its reflected light becoming indistinguishable from the background noise that characterizes astronomical observations at instrumental limits. Professional telescopes, equipped with the most sensitive cameras available to terrestrial science, record only empty pixels, where 3I Atlas once blazed with impossible brightness. The final confirmed observation occurs on a clear night in Chile, where atmospheric conditions briefly permit detection of a 20th magnitude point source that moves with the predicted angular velocity before disappearing forever into the stellar background. Yet the acceleration continues its mechanical progression according to mathematical laws that operate beyond human observation, carrying the visitor toward interstellar space with velocities that increase steadily under our sun's gravitational assistance. Orbital integration software projects the visitor's future trajectory through galactic neighborhoods where no human instruments will ever detect its passage. The same non-gravitational forces that created systematic deviations from Keplerian motion continue operating according to their unknown physics, propelling 3I Atlas toward the constellation Lynx along paths that trace invisible processes through the cosmic dark. The scientific literature undergoes its own evolution as researchers attempt to preserve their findings in forms that will remain comprehensible to future investigators. Research papers describe impossible observations using language constrained by current theoretical vocabulary, creating documents that future scientists may regard as primitive attempts to describe phenomena that transcend present understanding. Conference proceedings archive the debates and controversies that characterized humanity's first encounter with interstellar physics, preserving not only measurement results, but also the intellectual struggles that accompanied their interpretation. Theoretical physics experiences a renaissance of speculation as researchers explore exotic matter configurations, modified gravitational theories, and quantum mechanical effects that might explain the visitor's impossible behaviors. Mathematical frameworks that extend beyond established physics proliferate in preprint servers and theoretical journals, creating a literature of scientific speculation that may someday converge toward accurate description of interstellar object physics. Yet, none of these theoretical constructions successfully reproduce the full range of phenomena observed in 3I Atlas, instead explaining individual characteristics while failing to achieve comprehensive understanding. The psychological impact settles over the astronomical community like morning mist, transforming initial excitement about discovering impossible physics into contemplative recognition of scientific limitation. Researchers who devoted months or years to studying the visitor confront the sobering reality that humanity's most sophisticated instruments and theoretical frameworks proved inadequate to decode the message carried within 3I Atlas's mysterious behavior. The visitor's passage through our solar system becomes a humbling reminder of how much remains unknown about the fundamental nature of matter, energy, and the forces that govern cosmic evolution. Educational institutions incorporate the 3I Atlas observations into curricula that emphasize the provisional nature of scientific knowledge and the importance of remaining open to phenomena that challenge established theory. Astronomy textbooks acquire new chapters describing humanity's first encounter with interstellar visitors, using the observations to illustrate how scientific understanding advances through confrontation with anomalous data rather than simple confirmation of existing models. The visitor's legacy extends into pedagogical frameworks that prepare future scientists for the intellectual flexibility required to accommodate revolutionary discoveries. International collaborations strengthen as researchers recognize that understanding interstellar visitors requires global coordination of observational resources and theoretical expertise. The networks established during 3I Atlas observations become templates for future campaigns targeting similar objects, creating institutional frameworks designed to maximize scientific return from brief encounters with cosmic wanderers. These collaborative structures represent organizational evolution driven by recognition that interstellar visitors carry information too valuable to waste through inadequate coordination or resource limitations. Amateur astronomy communities maintain their own vigils for future interstellar visitors, equipped with instrumentation that continues advancing toward professional capabilities through technological democratization. The distributed observational network that contributed measurements during 3I Atlas's passage represents a revolution in citizen science participation that may prove crucial for detecting and characterizing future visitors during their brief passages through our solar system. These amateur networks provide observational redundancy that professional facilities cannot match through geographical distribution and dedication to continuous monitoring. Search programs undergo systematic enhancement as astronomers recognize that interstellar visitors pass through our solar system with much higher frequency than previously estimated. Automated survey systems designed to detect potentially hazardous asteroids acquire additional algorithms optimized for identifying objects with hyperbolic trajectories and unusual brightness characteristics. The techniques developed for 3I Atlas detection become templates for future discoveries that may occur with sufficient advance warning to enable spacecraft intercept missions. Spacecraft mission concepts proliferate in aerospace engineering communities as researchers explore technologies that might enable rapid response to future interstellar visitor discoveries. Solar sail propulsion, nuclear thermal rockets, and gravitational assist trajectories become subjects of intensive study aimed at reducing the response time between discovery and intercept from decades to years or months. The visitor's passage through our solar system catalyzes technological development that may eventually enable direct sample return from interstellar objects rather than relying entirely on remote sensing techniques. Philosophical implications percolate through academic communities as scholars grapple with the recognition that physical reality extends beyond current scientific description in ways that challenge fundamental assumptions about the nature of matter and energy. The observation that objects can simultaneously conform to and violate established physical law raises questions about the completeness of scientific theory and the possibility that natural phenomena operate according to principles that transcend human